Good evening, everybody. It's Monday, May 4th, and this is Nighttime Mathematics Radio. Well, the format of the show is always the same. Tweet your questions to @NightMathRadio on Twitter, and I'll try to answer them here live on the air. We've got one question already in, but if anybody has any other questions, now's the time to tweet them. Let's take 1 or 2 minutes, let people tweet in, then we'll get started with the show. This is Nighttime Mathematics Radio. Welcome back to the show, everybody. Well, we've got one question for the night, and the question looks like this. It's a question about the unit circle. And the question comes, well, suppose you're at an angle t such that, and I'll draw the picture out. So you're at an angle t such that you're actually at the point -3/5, comma -4/5. So you recognize this is a variant of a 3-4-5 right triangle, just divided out so that the hypotenuse will have length 1 as it has to, because it's supposed to be on the unit circle. And the question is, if this is angle t, what's the tangent of t? And this is the point. Questions like this tend to be the point where people realize they've missed something fundamental. Because when they first started learning trig, everything was always a triangle. You had nice little right triangles. You're told that from some angle side, say this is t, that you have the opposite side over here, the adjacent side here, and the hypotenuse here, and you're told that tangent, for example, of t is equal to opposite over adjacent. And then when you get to a problem like this, you look at this, and there's no sign of an opposite or adjacent anywhere. We've got an x value and a y value and nothing else. So the question is, what happened? Why are we looking at a weird point on the unit circle? How can we do this? How can we even figure out what a tangent means if we don't have an opposite side and an adjacent side? And the answer is, we switched what we mean by these angles. See, when we first looked at the unit circle, we always looked up here in quadrant 1. We took some point in quadrant 1 where we said, okay, there's my angle t. Now, when you're in quadrant 1, you notice the x value of the point is just exactly what we call the adjacent side of a right triangle, and the opposite side is just the y value. And so we defined all our trig values in here saying, well, if we're on the unit circle, that is, if x squared plus y squared equals 1, then we can write all the trig functions down in terms of x and y. Sine t is equal to just the y value in the unit circle. Cosine t is equal to the x value. Because remember, the hypotenuse is 1. So opposite over hypotenuse is just y over 1, or y. And finally, tangent t is equal to y over x. And you can go on and define secant and cosecant and cotangent if you'd like. So you notice at this point it looks like, well, all you've done here is played a game. We've drawn something in the unit circle and pointed out that the trig functions, as we've known them up to this point, can be used in terms of x and y. And now we're going to play the same switcheroo you play over and over again in mathematics. Over and over again in mathematics, you notice that what had been your definition is actually less useful than the consequence. And if we switch them, if we say we're not going to define these things to be what used to be the result, you get a much more useful definition. That's what we're going to do here. Rather than saying these are things that came about because we had sine and cosine and tangent defined in terms of opposite and adjacent sides, let's define sine, cosine, and tangent to be these things. Let's make this our definition. Say, our definition is if you're on the unit circle, then sine, cosine, and tangent are defined to be y, x, and y over x respectively. Well, the cool thing is that all the usual trig identities come right, the old trig definitions, you can get out of that definition, because after all, for any right triangle like this, with opposite, adjacent, and hypotenuse, you can find a similar triangle that's in quadrant 1. Because after all, if I have an opposite side and adjacent side and a hypotenuse, there must be a similar triangle where I can make the hypotenuse 1, and how can I do that? I divide all 3 sides by h. That gives me a similar triangle. It's not a congruent triangle, the sides are different, but a similar triangle, the ratios are all still the same. 1, O over h, and A over h. And now we notice, well, what's sine? By what's now our definition, the sine of this angle is the same as the sine of this angle. It's the same angle after all. And that's the y value, opposite over hypotenuse. The cosine is the x value, adjacent over hypotenuse. And the tangent is y over x by our new definition. That's now opposite over hypotenuse divided by adjacent over hypotenuse. We know how to divide fractions. That's opposite over hypotenuse times hypotenuse over adjacent. So it's opposite over adjacent. So you see, what used to be our definitions are now provable from what's now our definition, and what's used to be our consequence is now our definition. Why do we make that change? You say, well, if it's exactly the same, why do we care? Well, it's not exactly the same, and the reason is, if you're interested in angles that are bigger than 90 degrees or less than 0, we can still compute them from these definitions. Whereas, if I try to do it from this definitions, I'm done. For example, if I say, what's sine of 90 degrees? Well, by this definition, that requires me to have a right triangle, which has my usual right angle. Then at 90 degrees has another right angle. And then I apparently have to keep drawing these things drawing these sides until they meet. But of course, they're never going to meet. That doesn't make sense in terms of right triangles. You can't have a right triangle with 2 right angles. But, oops, let me scroll this up a little bit. With our new definitions, there isn't even a puzzle. 90 degrees is just right here. The point up here is x is 0, y is 1. So sine 90 degrees is our x value, so it's our y value rather, so it's 1. Cosine of 90 degrees is our x value, so it's 0. And tangent of 90 degrees is undefined, because it would be y over x, which is 1 over 0. So it's now undefined. So suddenly these aren't a puzzle. Suddenly we can actually say what these functions must be up there. And we can keep that going as far around as we want. So for example, in this problem, we're asked, what's tangent t? Well, if you're thinking opposite over adjacent, you're done. There's no right triangle here at all. The first angle you have is this enormous angle here. If you try to draw a right triangle with that, you're dead already, because this is more than 180 degrees already. That plus then you try to get a right angle, and that's 90 degrees. They have to sum up to be 180 degrees, so this isn't going to work. But in terms of these definitions, this is easy. It's y minus 4/5 divided by x minus 3/5. So that's minus 4/5 times minus 5/3. The minus signs go away because minus times minus is positive. The 5's cancel, and it's just 4/3. And again, as long as we use these definitions, it's not even a puzzle. This has happened over and over again in mathematics, and people often don't bring enough attention to it. You did this with exponents, because remember, when you first learned about exponents, you were told a number to a power is just that number multiplied by itself that many times. So, 3 squared is 3 times 3. 5 to the 5th power is 5 times 5 times 5 times 5 times 5. And then you worked out all these cool properties based on that. You worked out that if you take, say, a number to one power times another to another power, the same number to another power, you could just add the exponents. If I take a number to the first power, that's just the number itself. If I take a to the m over a to the n, I get a to the m minus n, as long as m is greater than n. And then at some point you go, okay, this restriction's annoying. I'll just cross it out and say, this is now our definition of an exponent. An exponent is a cool function which works like this. Anything to the first power is itself. The same number to two different powers is just the sum of the exponents. The same number divided by a number of a different power is the difference of the exponents. And from that, you can work out all the other cool things. Now you could say immediately what the zero exponent means. It's 1, because now you're dividing something by itself. Now you can immediately say what a fractional exponent must be, and so on and so forth. So it's worth watching for this trick, because we play it over and over and over again in mathematics. You realize that the definition you started with, which is usually motivated by some real-world concern, by some physical process or something, is actually less useful than some other definition, so we switch one for the other. And suddenly we get a much more powerful function, because these definitions we can use to talk about spring motions, to talk about business cycles, to talk about any number of interesting things, to talk about positions on the Earth, where the triangle definitions would prove useless because you can't go past 90 degrees. So it's a fun trick to watch where it happens over and over again in mathematics. This is Nighttime Mathematics Radio. Well, looking at Twitter, that was our only question for the night, so I'll probably end the show right here. So once again, in this strange world where all the classes have stopped, but the homework just keeps going on and on and on, keep tuning in at 9 p.m. or tonight 9:05 p.m. Pacific time. And I'll be here with all the math and all the strange loops from Apple's GarageBand that I can bring to bear. Good night, everybody. Stay safe. And keep doing the math.